In Year 11, we already looked at how to make a probability distribution table, something like this, using discrete data. Now remember, discrete data is data where each data point is a unique number that is separate from the number beside it, so they can be easily categorized. And we are today going to look at how to extend our knowledge into cumulative probability distribution tables. And this is a concept that we're really going to need so that we'll be able to work with continuous data in the next lesson. So let's have a look at what we've got. A probability distribution table lists the probability of some discrete random variable, big X, taking each possible value, little x. This is something we've already seen, but you might need to revise. You can consider whether you need to write that down or not. Now there's two ways we can write the probability. We either say big P, meaning probability of something in brackets, and we say the probability of the outcome is any particular one of these values. Or we can abbreviate it and use little p, x in brackets. So there's two ways to write the same thing there. Now in this example, we're tossing a coin 4 times and we're letting big X, that is the outcome, be the number of heads that are possible. So we're not actually carrying out this experiment, we're thinking about what's likely. So we're using theoretical probability, not experimental probability. Now I can calculate these quite quickly and easily by just thinking through what my tree diagram would look like if I were to draw one. And I in fact don't even need to draw the whole diagram, I've just got to imagine it. So I could start drawing it and easily reason that I'm going to have 1, 2, 3, 4 coin tosses. So the total number of outcomes out here will be not 2 or 4 or 8, but 16. So all of these probabilities straight away I can see need to be out of 16. Now remember, all of them will add up to 1, that's something that I know. So if you were given a bunch of these and one was missing, you could easily figure out what it was. Now there's only going to be one way that I can get no heads. That's if I've got 4 tails. And that would be this pathway, tails, 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 tails. There'll only be one of those pathways. So there's only one chance out of 16 of getting 0 heads or 4 heads, same thing. How many ways can I get 1 head? Well, if I'm getting 1 head, there's going to be 3 tails. If I'm tossing this coin 4 times, then either the first coin was heads, the second coin was heads, the third coin, or the fourth coin. And if you go ahead and draw your entire tree diagram, which I'm suggesting we probably don't need to do, we can just imagine the paths that we would take, there's going to be 4 different paths that lead to one of those outcomes. And if you were listing them, you would say, hey, I can get heads, tails, 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 heads, tails, 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 heads, tails, or tails, 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 heads. See how that's the exact same reasoning as the head could either be first, second, third, or fourth. There's only one of them. So that's 4 different ways it can happen. And just as I can get 1 head and 3 tails, 4/16 of the time, I'm going to get 3 heads and 1 tail, also 4/16 of the time. 1 plus 4 plus 1 plus 4, that's 10. That leaves me with only 6/16 left, so I can really just fill that one in using logic. All right, now we call this a probability distribution table. We've made these before. But what we're making now is a cumulative probability distribution table. So we need to add 1 more row. Now, what does cumulate mean? If I say you've accumulated a lot of something, it means you've added it or gathered it together. So that's what this is here. The cumulative probability table simply cumulates or adds the probabilities. So the way we write it, it's got 2 different ways we can write it. We're going to put function with a big F of x. But it's also called, I didn't leave quite enough space there, did I? Or the probability that big X is less than or equal to little x. It's a bit messy, sorry about that. Okay, what do we mean here? Well, we're saying what's the probability that the number of heads I get is less than or equal to each of these? Okay, well the probability that the number of heads I get is 0 or less, can't get less than 0, it'll have to just be equal to 0, 1/16. What's the probability that the number of heads I get is 1 or less? Well, it's going to be the probability of getting 1 plus the probability of getting no heads at all. So not 4 or 1, but 5/16. The probability that I get 2 heads or less, well, I need to add these 3 together. and you can see here why I didn't bother simplifying my fractions. It's much easier to add my 16ths if they're all having a common denominator. And continuing to add on, there's a 15/16 chance that I'm going to flip and get 3 heads or less. And then of course this will add up everything, so I'll get 1 here because it's certain that when I toss 4 coins, or 1 coin 4 times, I'm going to get 4 heads or less. That's a certainty. So this end column here of sum isn't really relevant, but we often have this column just so we can use this as a quick check that our actual probabilities add to 1. Now what do we do with this data? Well, we can make probability distribution histograms and polygons by building a graph that's got columns that are each of these heights and then joining the columns together to make a polygon. And we can call that polygon also a function, which is where we get the name PDF, a probability distribution function. We can also use the cumulative data to make a cumulative version of the same thing with columns that are these heights. And then when we join those together to make a polygon, we call it a cumulative, we leave out the P, cumulative distribution function, or a CDF. Now the reason we need to work with a different set of data when we've got continuous data is that we're not going to have a table like this. And the reason is we're going to have an infinite number of columns when we've got continuous data. So it's not relevant to look at the probability of any one outcome happening, because if you've got an infinite number of outcomes, the probability of any one of them is actually 0. Instead, when we work with continuous data, we need to look at the probability of getting something or less, because it's a way that we have of defining our problem in a way that it can be solved and we can get some answers.